Okay, so how exactly do you map a world that's entirely invisible? Have you ever wondered how scientists can look at a seemingly simple drop of liquid or a speck of powder and definitively say, ah, this is caffeine, or this is the exact drug molecule we need to cure a disease? Welcome to The Explainer. Today we are going to decode the ultimate mystery, the invisible molecular realm.
We are unpacking the Invisible Toolkit, from molecular dance to drug design. We're going to take a fascinating journey today, starting from the fundamental physics of light and matter and tracing it all the way up to life-saving applied pharmacology.
Here is our roadmap so you know exactly where we're heading today. First, catching the invisible wave. Second, the dance of atoms. Third, reading chemical fingerprints. And finally, modeling the molecular glue.
All right, let's dive right into part one, catching the invisible wave, unmasking light.
So to understand how we actually see this hidden world, we've got to start with electromagnetic radiation. Sounds a bit complicated, right? But it's basically just two mutually perpendicular electric and magnetic fields oscillating at right angles. It's the absolute foundation of how we probe the microscopic world.
Picture the anatomy of this wave. You've got the electric field oscillating up and down, while the magnetic field oscillates side to side. They travel together completely in phase at a constant velocity. And that velocity? Yeah, it's the speed of light. This invisible traveling wave is literally the tool we use to reach out and touch molecules.
Moving right along to section 2, the dance of atoms, springs and vibrations.
Now, once we have this wave of light, we need to know how it actually interacts with physical matter. Don't picture chemical bonds as rigid little sticks. Instead, think of them as tiny vibrating springs. They're totally governed by Hooke's law. So the physical stiffness of the bond, what physicists call the force constant, along with the mass of the attached atoms, dictates exactly how that molecular spring is going to bounce and vibrate.
Because these atoms are hooked together by these tiny springs, molecules have what we call degrees of freedom. Basically, they move in three main ways. First up is translational, which is just moving straight through space. Then there's rotational, spinning around on an axis. And finally, vibrational, the actual stretching and bending of those atomic springs. It's this third movement, this vibrational dance, that gives us the key to reading their hidden signals. Think about water molecules, for example. We're looking at two distinct types of vibrational stretching here, symmetric and asymmetric. In symmetric stretching, the hydrogen atoms move in and out together, totally in sync. In asymmetric stretching, one moves in while the other stretches out. But here is the absolute crucial point for our toolkit. For us to actually detect these vibrations using infrared light, the movement absolutely must change the molecule's electric dipole moment. If the dipole doesn't change, the vibration is completely invisible to our infrared wave.
Carbon dioxide is a perfect example of this rule in action. A resting CO2 molecule is just a perfectly balanced straight line with zero net dipole moment. If it stretches symmetrically, pulling equally on both sides, it stays completely balanced, meaning no infrared signal is generated at all. But during asymmetric stretching, one carbon-oxygen bond gets longer than the other. That perfect balance is broken, an active dipole is created, and boom, we can instantly detect it.
Of course, out in the real world, reading this molecular fingerprint isn't always super clean. Scientists constantly have to play detective to decode a few glitches in the data. For instance, we might run into overtone bands, which are essentially multiples of the fundamental frequency, kind of like musical harmonics. Or we might see combination bands, where two completely different fundamental bands absorb energy at the exact same time. We even come across this weird thing called Fermi resonance, where two bands mysteriously show up close together when we were only expecting one. It's really like a giant, beautiful puzzle.
All right, that brings us to section 3, reading chemical fingerprints, the tech evolution.
So how do we actually build the machines to capture this microscopic, glitchy dance? Well, historically, scientists used dispersive spectrometers. Starting way back in the 1940s, these were pretty clunky machines that scanned incredibly slowly through wavelengths using physical slits and prisms. But then came the absolute game changer, Fourier transform spectrometers, or FTIR. These modern machines are insanely fast and produce super high-quality data. And they do it by totally ditching those physical slits and using a brilliant piece of tech called an interferometer.
Let's demystify how this actually works. Inside the Michelson interferometer, radiation from the light source hits a semi-reflecting beam splitter. Exactly half the light reflects onto a fixed mirror, while the other half passes right through to a moving mirror. As those two beams bounce back and recombine, they physically interfere with each other. Sometimes they destructively cancel out, sometimes they constructively build up. This creates a really complex interference pattern called an interferomogram. That pattern emerges from the machine and is rapidly decoded by a computer using a mathematical process called Fourier transformation. It's literally a marvel of physical engineering and high-level math working in total harmony.
But even with all this incredible tech, we still face some frustrating real-world challenges. Take the issue of atmospheric interference. The very air sitting inside the spectrometer, specifically the ambient carbon dioxide and water vapor, naturally absorbs infrared light, causing massive, jagged spikes in our readings. We literally have to calculate and mathematically subtract all this huge background noise just to see the pure fingerprint of the tiny sample we're actually trying to study.
But once we clear away that atmospheric noise, the results are stunningly precise. Just think about this number, 1656 inverse centimeters. That is an exact, highly unique infrared absorption fingerprint. And here's a fun fact for you. If you had coffee or tea this morning, you ingested the specific molecule that produces this exact signal. That 1656 mark, that is the unique chemical fingerprint of caffeine.
Okay, final stop, Section 4. Modeling the molecular glue from physics to pharmacy.
Now, we're going to pivot from just detecting these molecular fingerprints to actually applying this physics to real-world pharmacology. The research here is incredibly clear. As the source material explicitly states, hydrogen bonds play a crucial role in determining the specificity of ligand binding. Now, ligand binding is really just the fancy technical term for how a medicine chemically attaches to its target inside the human body. This quote marks our big shift from abstract physics into the very real, very high-stakes world of computational drug design.
To figure out how to make drugs bind perfectly, modern scientists rely on a highly advanced computational method called GRID. GRID is specifically designed to detect energetically favorable ligand binding sites on a target molecule of a known structure. What does that mean in plain English? It means it uses incredibly powerful computers to predict exactly how and where a potential new medicine is going to click into a disease target inside the human body.
And it doesn't just make a wild guess. GRID calculates this using an empirical energy function that looks at three highly specific forces. First, the Lennard-Jones term, which deals with your basic atomic attraction and repulsion. Second, the electrostatic term. But researchers quickly found that relying only on those simple spherical forces just wasn't cutting it for modeling complex biology. The computer absolutely needed the third component, the hydrogen bonding term.
So why is that third term such a huge deal? Well, because as we learned earlier with our water and CO2 molecules, these aren't just static little dots. They are precise geometric structures. Hydrogen bond strength depends heavily on both its physical length and its precise three-dimensional orientation. Remember those tiny vibrating springs and the exact angles of the atomic dance we were talking about earlier? That exact physics, that precise microscopic geometry, is what ultimately dictates whether a newly designed drug will successfully bind to a virus or a mutated cell and actually cure a disease.
So you can see how beautifully it all connects, right? The invisible physical vibrations that we detect with infrared light are the exact same fundamental forces that allow life-saving medicines to work in our bodies. Which leaves us with this final thought for today's explainer. If we can already decode the invisible dance of atoms to build better, more precise drugs, what other hidden symphonies are out there just waiting to be discovered? Thanks for hanging out and exploring this invisible world with us today. Keep learning and keep looking deeper.